Hello. So, in the next hour, I will talk about causality. We have a lot to cover, so we'll go ahead and get started. I received some funding from NIH for some of the multicentric trials. I have no conflict of interest relevant to this talk. It's, as you may have guessed from the title, it's a research methodology talk. It can get very boring. And to keep things lively, I've inserted picture of my dog at random places. So this is Mr. Oreo. Um, and I also find that it's easier to understand these kind of talks when you have an ability to pause and rewind. So I've also recorded this and you can watch it on the recorded ground rounds, but it will also be available on YouTube and on Twitter. So, what is causal inference? Causal inference is finding the cause of things, and if you have done clinical research, you have done causal inference. Um, what what it is in it is if the drug A causes any change in outcome, or does a disease causes this symptom, or does this symptom cause disease to have worse outcome. Uh, the Wikipedia describes it as a process of determining the independent actual effect of a particular phenomenon that is a component of a larger system. So statistics and causal inference have a contentious relationship. Statistics is relatively new science, and Francis Galton and Carl Pearson and R.A. Fisher, these are the founding fathers of modern statistics. Relationship between two variables or correlation was first described by Galton, and he was trying to do some anthropometric measurements. He also uh, described regression when he was comparing the heights of parents versus their offsprings. And then the correlation coefficient, the Pearson rho that we quote, was developed by Carl Pearson. But very quickly, the, the founding fathers of statistics forbade the use of causal language in correlation. And they are considered even now off limits in any non-interventional trials, and mostly for good reasons, because we have heard correlation is not causation, and even in middle school statistics we're taught correlation is not causation, because otherwise ice cream sales would be associated with crimes, and chocolate consumption would be associated with or chocolate consumption would cause Nobel Prize winners. So correlation is not causation. And in clinical observational trials, whenever you write papers, and even if there is any causal terminology impact of due to, they're all the reviewers will make you scrub it. But that doesn't prevent readers from jumping to causal conclusions. And this is, I follow a lot of statisticians on Twitter, and this guy um, wrote this recently. What about causal language in medical research? Well, one needs to be careful with causal language. So we should not talk about causes. No, we are talking about causes. Cause and effect are of primary interest. So we'll just stay away from explicit causal language and imply it. Um, So again, data, right? Statistics is all about data. Fisher is described statistics as a study of methods of the reduction of data. And the Statistical Society of London, 1834, um, almost 200 years ago, says data were to receive priority in all cases over opinions and interpretation. Data are objective, opinions are subjective. But when we do causal analysis, we will realize it's not just about data. We have to uh, understand the processes that produce the data. Um, Another quote from Twitter: "The unfortunate truth from data is that nothing much can be done with it until we say what caused it." In itself, data is profoundly dumb. So, language of causation. Causation was developed by um, uh, Judah Pearl and colleagues, and this is not a new science. It's 1970s, 80s, 90s during the evolution of computer science. So he's a computer scientist. Uh, it involves two things. It involves causal diagrams to express what we know, and it involves a symbolic language, which is based on probability theory, algebra. And it goes like this. If you want to see the effect of a drug on lifespan, we express it as probability L given D. But if you're doing an interventional trial, we express it as probability L do D. The do operator signifies that we deal with an intervention rather than a passive observation. Because if we let the patient decide or we let the doctor decide to give somebody a drug, then there are a lot of factors that may influence that decision. So PL given D is not the same as PL do D. And causation has a lot. What we will talk about here is very elementary causation. I probably understand 1% of causation, and people do the whole PhD in causation. And causation has uh, a lot of usage. The Bayesian networks that were a part of causation are a part of machine learning and artificial intelligence. So, um, but what we will cover here is primarily the graphical language and not, and we'll stay away from the math as much as possible. Okay, so randomized control trial or PL2D is how you can apply causation. But there are many situations where randomized trials are not possible for ethical or um, uh, realistic point of view. So what do we do? So we measure, how do we measure causal effects in observational studies? One of the things we do is to adjust control for the confounders. And how do we control for the confounders? Well, there are a lot of things you can do: stratification, you can do propensity score matching, you can do standardization, or you can do regression. It's not a statistics talk. We won't go into detail about statistics or regression, but this is one of the things which actually made me interested in causal inference, is when you are writing code for, say, linear regression in R. It is fairly easy to do. It's like a one-line code. As the model is an equal to sign in our linear model, and you put in length of stay with opacity, and then after that you just add on the variables that you want to control for in a multivariable regression. Uh, it can be linear, it can be continuous variable or categorical variables, and specify the data, and it will give you all sorts of coefficients. The 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 difficult part is not to write the code for it. The difficult part is how to select the variables. And when I was doing it, I would realize that just changing one variable here and there sometimes can change the whole results. And in the field of null hypothesis significance testing, as we live in the era now, the p-value is of paramount importance. Uh, so 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 that leads to a lot of p-hacking and p-hacking, and I thought that that can't be right. And even now, many investigators would think that more control is better. Like we'll write it in our paper that our paper is better than the other papers because we have control for more variables. But that's what is called as a garbage can regression, another term that I got from Twitter. And investigators also often assume linear relationship without explicit justification. So we won't talk much more about regression and p-hacking here. That's a topic of a separate rundown, probably next year. So we'll talk a little bit about smoking and lung cancer. So we are in 2023, and nobody would think twice about smoking, causal relationship between smoking and lung cancer, but you would know that the whole causation between smoking and lung cancer is based on observational data. There is, because of ethical reasons, even in 1950s, there was no randomized controlled trial of smoking with lung cancer. So there was no P cancer do smoking kind of analysis ever done. But in 1950s, when the statistics field was developing, this was not the case, and Fisher was still alive. So Dahl and Hill's paper came out in 1950s, and Fisher didn't believe it, and there were 19 more papers came out on this, and people were like, hey, look, 19 papers all saying smoking causes lung cancer, and Fisher was still not having it. And he said that repeating a biased study 19 times does not prove anything. It's still biased. Ultimately, the debate was settled by 1963 with the Surgeon General report. We'll talk intermittently about smoking in various examples throughout this talk. So, jumping into the graphs, which are the main topic of this talk. What is directed acyclic graph, or DAG? Directed acyclic graphs are dot and arrow pictures that summarize our current scientific knowledge. Dots are quantities of interest or variables. Arrows are known or suspected causal relationship, or which variable listens to the other variables. So this is a terminology in DAG. You have a variable X and a variable Y, and variable Y is the cause of variable X. If variable Y listens to variable X and changes its value based on what it hears. So that's variable X, variable Y. But all of this, you will see a lot of arrows and DAGs that I have made in this talk. But the causal model is more than just drawing arrows. Behind every arrow is a mathematical probability that can be represented with functions. We will not go into the math part of the DAG in this talk. Many reasons. One of it is I don't understand it. All right, so this is the first causal diagram. Here is, these are the nodes, right? These are the variables, variable L, A, Y. Variable L causes variable A causes variable Y, and variable L has an effect on variable Y, which is independent of the mediator A. So these are the nodes, and these are the arrows. These are also called as edges, and this is called a path. A path does not have to follow the direction of the arrow. So there is a path from A to Y also. So there is a path from A to Y. This is a directed path. And then this is called the backdoor path, which goes from A to L to Y. So that's also a path. And then this graphs are called acyclic. This is directed because there are arrows have directions in them, and it's acyclic because L causes A causes Y, but Y cannot cause L, so a variable cannot cause itself. The other question is, how do we draw the DAG? We draw the DAG using our expert knowledge about the problem under study. There's a lot of terminology. There's a lot of ancestor terminology in DAG. So if two variables causes a child, they are the parent of the variable. So if this is an exposure and there is a cause of the exposure, then that's the ancestor. And then there is a outcome, and outcome has causes something, so that's the grandchild. And then the parents can be related to each other, or parents can be not related to each other. If the parents are not related to each other, it's immorality. not my term. It's a standard graph terminology. And if the parent causes the child, and then a parent has an ancestor, and ancestor is also related to the child. So that is the backdoor path from a parent to child going through this ancestor. And the backdoor path in this program that I made these graphs called DAG where the backdoor paths or biasing paths are color coded, and it is coded as pink, and the causal paths are green. Okay, so common causes. What's a common cause? Suppose we did a randomized control trial on aspirin A to prevent stroke. So aspirin causes or not, doesn't cause stroke. So aspirin to stroke is a direct arrow. But instead of randomized control trial, we collected a retrospective study on whether or not they had taken aspirin and if they had stroke or not from the EMR. Right? We got aspirin yes or no, stroke yes or no. So in this situation, you will have an arrow from aspirin to stroke, but you would realize that there would be common cause. For example, if a patient has coronary heart disease, they would be more likely to take aspirin, and the patients with coronary heart disease are also more likely to have stroke. So there is a common cause between exposure and outcome. So that is what we refer here as the common cause. So that's the coronary heart disease. The in in a randomized controlled trial, whether or not a person takes aspirin has no causes, and it's based on a flip of a coin. But here, there is a cause that causes you to take aspirin. So exposure is not random. Exposure assignment is not random, and there is a cause of exposure assignment, and that is what we need to control for. And that is what makes the observational studies so much different than randomized controlled trials. So confounding is the pain of observational data. Another example, which we talk about this course, which I learned a lot from its edX course from Miguel Hernan. We collected data on 1,000 patients of a population, and there are three variables: lung cancer, yes, no. So all the patients are listed in rows. Lung cancer, yes, no. Yellow finger, yes, no. Smoking, yes, no. Now, we know that there is a arrow from smoking to yellow fingers. If you like smoke a lot, then your fingers will become yellow if you're holding the cigarette. And then smoking has an arrow from smoking to lung cancer. But in a study like this, because of a common cause of smoking, of yellow finger and smoking to lung cancer, if you try to find an association between yellow finger and cancer, you will find an association. Because there is a path going from yellow finger to cancer. And how do we control for it? You control for it by by adjusting for it, and by many methods. For example, stratification. You only include patients who either smoked or not smoked. In that way, you can block. This is called blocking the backdoor path. In common statistical language, we'll call it adjusting for it, or controlling for it, or control for smoking. In DAG terms, we block the backdoor path between the. All right, moving on, the next thing is selection bias. Selection bias is a little bit difficult to understand as compared to confounding, which is a little bit easier. Again, we have 1,000 patients, and we took a data on cancer, yes, no, and whether or not you have environmental factors, yes, no, genetic factors, yes, no. Now, your cancer, it can be caused by genetic factors and an environmental factor. So these are common effects. They have this is an outcome of cancer. So they have a common effect of genetic factors, environmental factor is to cause cancer. So cancer here is is what we call as a collider, or a common effect. And in case collider in a DAG is a very special kind of node because it blocks the flow of information when it is not conditioned on, but it allows the passage of information when it is conditioned on. So if you're in a situation like this where you just collected data on 1000 patient cancer, yes, no, environmental factor, yes, no, genetic factor, yes, no, you will not find a relationship between genetic factors and environmental factors uh, if the study is not conditioned for, and you should not condition for cancer, because if you do condition for cancer and you only select patients who have cancer, now you will find a relationship between genetic factors and environmental factors. And why is it so? Because either genetic factor cause cancer or environmental factor cause cancer. So patients who have genetic factors are less likely to have environmental factors to have cancer. So if you see a relationship, you will find a negative correlation between genetic factors and environmental factors, even though no such correlation exists. So this is called a common effect or a collider. And this kind of bias is called a collider stratification bias because it's stratified on the collider. But that also is not restricted to the collider. The collider stratification, even if the collider has a child or a descendant, and you stratify for that, you will still introduce bias. So here is an example again. Cancer, you instead of stratifying for cancer, yes, no, you also collected data on whether or not they had cancer surgery done or any kind of surgery done, because you had that information and you put that in the model. Now again, you will introduce a bias because the descendant, or even if you condition for the descendant of the common effects, the path will be opened. Okay, so after knowing through common causes and common effects, we can now talk about the D-separation rules. There are just 4 of them, and they help us interpret the graphs. Basically, just summarizing what we've already talked about. This is complicated language, but what it means is the collider, uh, if there is a collider, the path is blocked. So if there, as long as there is no variables being conditioned on, if there is a collider in a path, that path is blocked. And a path that contains a non-collider that has been conditioned on is blocked. So this is not a collider, this is a path between A and Y. B is a mediator on the effect of A and Y. And if you condition on B, then you block this path. You will not find a causal effect of A and Y because this is a mediator, and you put a mediator in the model. You should not put a mediator in the model, and we'll talk about that. A collider that has been conditioned on does not block a path. We saw that cancer, environmental factors, genetic factors, cancer, it is conditioned on, it does not block a path. And a collider that has a descendant that has been conditioned on does not block a path. So this is a descendant of this collider that you condition on, it does not block the path. Okay, birth weight paradox. So we know that smoking babies of smoking mothers weigh less than average than non-smokers. We also know that low birth babies have a much higher death rate than normal birth weight babies. But Yerusami in 1971 published a paper which showed that among low birth babies, the babies who had smoking mothers had a better survival rate than babies whose mothers were not smokers. So he wrote that in his paper, 1971, after the Surgeon General report and after the science was settled, that these paradoxical findings raised out and argue against the proposition that cigarette smoking acts as an exogenous factor which interferes with intrauterine development and fetus. Uh, and we'll see how DAGs can help settle this debate. And this is from 2014 that DAGs were used to settle this report. So this is how you represent this DAG. Smoking is associated with birth weight. Smoking causes smoking. If you smoke in pregnancy, you will have low birth weight babies. Smoking is associated with infant mortality. Uh, If you smoke during pregnancy, the chances are higher that you will have infant mortality. But there is another variable that is congenital anomalies. So if you have a congenital anomaly, you will have a low birth weight, and if you have congenital anomaly, you can also have you will also be there is much higher likelihood of mortality. So there's a path from smoking to here, and there is a path from smoking to birth weight. This, however, is a common effect or a collider. So this path from smoking to birth weight to birth effect to infant mortality is blocked. However, if we condition on the birth weight, like only taking low birth babies, which is what Hiroshima did, what happens now is that this path becomes open. So now you have a path between smoking, birth weight, birth defect, and infant mortality. And now it's conceptually easy to think also. There are two causes of low birth weight babies: smoking mothers or congenital anomalies. The chances, if you're low birth weight babies and your mother was not a smoker, the chances are more that you are low birth weight because you have congenital anomalies. And while smoking causes infant mortality, congenital anomalies cause mortality at much higher rate than smoking. So not only this backdoor path negates this effect, it takes it to the other direction, and it appears that smoking is beneficial uh, for mortality if you are a low birth weight baby. But sometimes this we do quite often, and so I pointed to out here is sometimes we do not have a data on confounder. We know that A causes Y, and there is a confounding variable U which also causes Y, but we don't have a data on U, so we can't control for it. So what do? We find a variable L which may be strongly associated with U, not and we control for L. So this is what we do. We want to control for socioeconomic disparities. It's a construct, we can't measure it. So there are surrogate measures for socioeconomic disparities like race and ethnicity or insurance status, zip codes, and all those kind of things. And though we measure them, they never completely eliminate socioeconomic disparities, but we are able to make some sort of statements about it. All right, there is another example, multivitamin use and birth defects. So we know that folic acid use will reduce neural tube defects. So multivitamin use during pregnancy will reduce birth defects. But if you do a observational study on this, again, 1,000 patients, multivitamin use, yes, no. Do you have birth defect? Yes, no. There is a confounding variable, which is maternal education. Because if you are an educated person, you are more likely to take multivitamin, and you are also probably more likely to do other things which would prevent birth defects, like not smoking, not drinking. So there is a backdoor path. So in a study like this, you should control for maternal education. And if you control for it, that path gets blocked, and you can establish causal relationship. But what if we are collecting data, and it's very easy to collect data because you're extracting it from some sort of database, and you also collected data on birth weight. So now you have multivitamin use, neural tube defects, maternal education, but I want to control for more variables. So I think I want to put a birth weight also in the model. Now, this part we talked about, but multivitamin use may also be associated with birth weight, because if you're taking multivitamin for again you are because of a variety of reason of healthy lifestyles, you probably have an association with birth weight. And of course, birth weight, birth defects or congenital anomalies have a relationship with birth weight. So now, birth weight cannot be a cause of multivitamin use because it comes after. And here it's a in this path from multivitamin use to birth defect, it's a collider because it goes from here, collide, and it's a collider, and then it goes backward. So in this case, if you adjust for it, you will open this backdoor path. So in this situation, you should not be adjusting for birth weight. You can adjust for maternal education, but not for birth weight. So this is one of the good important reason for using DAGs is you identify based on your causal language or causal knowledge which variables you need to adjust for and which variables you should not adjust for. Okay, now selection bias is a little bit complicated. Some studies will always have an arrow from Y to C. So these are the studies with outcome-based selection. These are the case control studies. We select people in the study as cases based on some outcome. So this is Y is the outcome and C is the selection of the study. So selection is based on an outcome. The probability of selection bias now is very because if you already selected cases based on it, and if you're also selecting controls based on some sort of outcome, and so then you can introduce bias very quickly. So an example of this is hormone therapy with lung cancer. So we want to study if hormone therapy has an effect of lung cancer Y in women after menopause. So we did a case control study. We find a random sample of women in a city with cancer, and these are cases Y equal to 1. And then we selected a random sample of women with lung cancer Y is equal to 0. So this is great. We can do this kind of study. Selection is based on, there is an arrow for lung cancer to selection because women with lung cancer are more likely to be selected in the study. But if the selection is also dependent on the treatment, then you can have a bias. Suppose it's very hard to collect the controls from a general population, like how will you find a control? So, and easier is to just select the controls from patients who are hospitalized because we go and talk to them. And suppose we say patients with hip fractures. Now, hormone therapy prevents hip fractures. So there is an arrow from hormone therapy to hip fractures, and hip fractures has an arrow to selection. So now the hormone therapy patients have greater probability because hormone therapy prevents the hip fractures. So hormone therapy patients have a greater probability of being cases than controls because the patients who have hip fractures are less likely to have received hormone therapy. So the controls are less likely to have received hormone therapy while we're doing a case control study with lung cancer and non-lung cancer, and controls already have low probability of getting uh, um, hormone therapy. So you have introduced a selection bias. So this is a selection bias because of inappropriate selection of controls. And this kind of selection bias where the two diseases are not related to each other in the population, but they are related in the hospital is called the Parkinson bias. Okay, this is so far we have only concentrated on the observational studies. Randomized control trial we think are free of bias, but even these biases can and creep up in randomized control trials also. Randomized control trials are very great for variable selection at assignment to the groups, but after assignment uh, there can still be problems. For example, loss to follow-up. Loss to follow-up is very common in long-term randomized trials. So you're doing a trial on HIV drug, HIV yes, drug yes, or placebo, and then you are asking them to come back in a year to see if they develop AIDS, yes, no, right? Um, so, but some people will not come for follow-up because of many reasons, and if they will not come, then they would be censored. Um, if they do not come because of random reasons, then it's random, it's fine. But if they do not come because they develop AIDS or because they develop some sort of symptoms, then that's a problem because now you have an arrow of censoring from treatment to the health status of the patient and the health status to outcome AIDS, uh, and 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 then you can introduce bias because the people, for example, who got placebo were more likely to develop AIDS, and they have a larger dropout than the patient who got the HIV drug. So this is a follow-up study, which also in even randomized control trials you can lead to bias. Then there is measurement error. Uh, this is also important to know because this comes up quite often in our observational study, because uh, not everything can be measured, and not everything that we measure can be measured accurately. We are always have errors. So, for example, we are measuring the impact of aspirin on outcome, liver toxicity. Aspirin is A and liver toxicity is Y, and we are obtaining the data from the EMR. So what we want to measure is aspirin on liver toxicity. What we are actually measuring is A star, which is what you have the data on, and Y star, which is the liver toxicity, which you have the data on, because you may be prescribed aspirin, but you don't take aspirin. So EMR says you take the aspirin yes, but in actually you are not taking aspirin, so it's aspirin no. So this is a misclassification error. And then these errors, the difference between A star and A is the UA, and the difference between Y star and Y is UY. And and there are now 4 kinds of measurement errors, which we'll talk about. One is a situation where you are assessing this in EMR, but different people enter this data in the EMR, or uh, aspirin use one you are getting from EMR, and one you are getting from phone interview. So both have errors in them, but they're not related to each other. But what about both this aspirin use and liver toxicity you are getting from a phone interview? The one person is asking you, making a phone call and say, hey, in the last year, did you take aspirin? He said, yes, no. And he also asked, oh, but do you have liver damage? Yes, no. So, so now there is an error. And this error can introduce a bias, and you can find a relationship between A star and Y star because of this common cause UAY, even though there is no relationship, there's no relationship between aspirin and liver toxicity. So this is a independent error, and this is a dependent error. And then there are differential and non-differential errors. So what that means is whether or not the error in the measurement of a cause or an outcome is dependent on outcome or the cause. So here, for example, we are making this assessment on the phone call, and you're making assessing aspirin with dementia. But how you are doing it, you're making a phone call. So making a phone call and say, hey, did you take do you have dementia or not? Yes, no. And do you remember taking aspirin in the last year or so? So obviously, if you have dementia, then the chances are that you will not remember did you take aspirin or not. So there will be a measurement error in aspirin use based on the outcome, dementia. So that's a differential error. And this is also another differential error, which is a follow-up study. And I am a doctor, and I am trying to see if aspirin causes liver toxicity. So I am going to follow up the patients, even if I'm not doing a prospective study. I know that aspirin may cause, for example, bosentan causes liver toxicity. If I give somebody bosentan, I will follow these patients very carefully to see if they develop liver toxicity or not. So I will have more data, while if I'm not taking bosentan, then I will not. So you will the measurement error on liver toxicity is dependent on whether or not he was assigned to the group aspirin or he took aspirin. So outcome error is dependent on the treatment. So that's a differential error. And how do we control for measurement errors? We control for them by making our measurement better, or just knowing that these kind of errors can happen. And particularly the differential errors and dependent errors are harmful because they open biasing pathway. The independent errors are there, but since they're not related, you won't find a relationship between A star and Y star under null. Okay, the last thing is mediators. Mediators mean if the drug A affects the heart disease Y, so there is an arrow from A to Y. But what if the effect of drug A on the heart disease Y is because the effect of blood pressure? So now you have an impact. There is a mediator, blood pressure. But it's also possible that there is a direct effect. So you can have a direct effect of drug A on Y, and there is an indirect effect on blood pressure. So there is a total effect, there's a direct effect, and there's an indirect effect. And why is the mediator important? So controlling for the mediator, and this is an example I borrowed from one of the papers in 2018. We are interested in this causal pathway. We are interested in the causal pathway of education on income. And we think that the intelligence, child's intelligence, impacts education, and child's intelligence also impacts the income that you will have. So there is an arrow from child intelligence L to education and an arrow from intelligence to Y. And because it's a common cause, you control for it, and you will find an association, you find a relationship between the education that you receive and the income that you are earning. But you also have data, so that's the childhood intelligence, but then you also have data on adult intelligence. So you can have an education, for example, uh, I'm very educated, but I'm not very intelligent, so that's why I'm not earning a whole lot of money. So intelligence is a mediator between the education and the income. Uh, it, but you can also imagine that there are other confounders which are impacting the intelligence and the income. And we don't even need to know those or measure them. It's an unmeasured confounder, but it's impacting the mediator and the income. And adult intelligence is hard to measure, so we don't have the measurement of it, and we measure that based on performance in chess, for example. It's a surrogate measure. So now, since we now in this situation, it's a mediator, but the path between education and income is this, and this path, which is going through this mediator, which is also uh, uh, not blocked, but this path, which is education to income, going through this unmeasured confounder is blocked. So education, intelligence, confounder, and income, because there is it's actually a collider here. But what if we adjust for it? If we adjust for it, now you open this biasing path. So education, intelligence, unmeasured confounder, and income. So in this case, adult intelligence, you should not control for, because it's a mediator. And the reason I put this is we do this quite often, that there are two variables, and one variable is causing the other variable through a mediator variable, and we need to know whether that variable is a mediator or a confounder, and there are statistical methods to do it, and I've done it in one of the trials, and those methods are based on statistical association. So in a causal language talk, they're kind of a off topic, but identifying mediator for mediator analysis, which is a statistical field in itself. So controlling for the mediator. And then lastly, one more talk about mediator is the front door talk criteria. We talked a lot about the back door criteria, but Pearl describes a front door criteria. And we'll take the example of smoking and lung cancer. So we think the main criticism in the causal relationship between smoking and lung cancer, which Fisher used to believe, is that there is a smoking gene, and smoking gene is associated with why you will become addicted to smoking, and smoking gene is also the cause of lung cancer. So smoking does not cause lung cancer, it's the smoking gene which causes lung cancer. Um, and there is no way to measure smoking gene, of course. It wasn't there in 1950s, and it's not there 2023, so it probably doesn't exist. But say it does exist, and we can't measure it, but we are assuming here that the effect of smoking on lung cancer is because of a deposition of a substance called tar. And all the effects of smoking on lung cancer is through tar, and we can measure tar, and smoking gene does not influence tar. Now we can use front door criteria to tease this out, because we want to know P, lung cancer, do smoking. So if we want, first we will find that the P, tar, smoking, and that's easy because there is no backdoor path from smoking to tar because this is a collider here. So all we do is P tar smoking, P tar no smoking. When we want to do P cancer tar, this you can this is a path from there, smoking gene lung cancer. So but we can measure smoking, so we can control for it. So P cancer tar we can control for it, and then using some sort of algebra we can come to P cancer smoking. It's very hypothetical example, but this is a front door criteria which can be used if a right condition exists. So which is this: anytime a causal effect of A and Y is confounded by one set of variable U and mediated by another set of variable M, and the mediating variable is shielded from the effect of U, then you can estimate the A's effect on Y, Py to A from observational data only. This sort of front door criteria has not been utilized yet for solving any causal problems. Last thing is causal discovery. So what if we don't know the causal pathway? What if we don't know what we don't know? In that case, we can use our data to help us learn the causal structure. And using data to learn the causal structure is known as causal discovery. So first we draw a DAG from no arrow between A and B. But if our data says a strong association, we have ruled out a causal DAG of A, no arrow B. So we ruled out A, no arrow B. This is not possible because there is an association. But here is the problem. All we know is A and B have an association. The exact causal structure can be very different. Several causal structures are compatible with the same data. So we can have A arrow B, we can have B arrow A, we can have A and B associated because of a common cause L. A and B can be associated because we have condition on a common effect L. And another problem is how do we distinguish an association due to a causal structure from an association due to chance? So causal discovery is very different from causal inference and much more complex and for this talk. So we won't go more in causal discovery. So this is all brief summary of the DAG. What do I use DAG? What's the benefit of DAG? They're nice pictures. What do I use for? It explains the pattern in the data, right? Which variable is associated with which variable. And then, as I mentioned before, when you're trying to control for it, what variable you select for, you have to describe it in the manuscript. How did you select the variables? And you know, if you select the variables with the DAG, it makes a little bit more robust explanation. And then you can also be transparent about the various biases in your study design. What I've not done yet, and will do in our future studies, is adjustment by design. So you can adjust it by regression, but if you design it in a way that you stratify your study population into one or the other groups based on the confounder, then that's called adjustment by design, and it is so much better than adjustment by regression. Identifying which variable is a mediator and identifying selection bias is also important, and these things needs to be done at the time of design, and then using a do calculus for mathematical model building. Obviously, DAGs have very serious limitations. Causal inference relies on assumptions, and assumptions are a problem. With no control over the treatment assignment, we need to model it. And when we say we model it, what we mean is that if we control for variable X, Y, and Z, we think that the two groups are so similar that the treatment assignment was done at random. And that's assumption that is almost guaranteed to have an error associated with it. And garbage in, garbage out rule applies here also. If you cannot squeeze data for causal confusions if it's not there. Another thing that I learned from Twitter is there is no magic in statistics. It's the first rule of statistics is there is no magic. And the second rule of statistics is that you cannot bypass first rule by clever math. Okay, and uh, but there's always a but, is that since all models are wrong, should we be concerned about, small problems? And well, there are big problems that you can solve. So big problems, or the tigers, the confounders, the selection bias, the mediator bias, this you can control for. There are always going to be unmeasured confounders, but at least you can identify big tigers and control for them. So now I will not have time to go over details of these DAGs, but I will show uh, some of my studies over the last few years where I have actually used DAGs and published DAGs along with the papers. And as I have learned more about DAGs, my DAGs have become better. Uh, I'm sure they still have errors in them, and they're also made in Word as opposed to the DAGity program, so they look different. And in this kind of, if you do it in this way, when you put a box around a variable, that means you condition for it or adjust for it. So this is obesity and critical illness from COVID-19, and all these variables are adjusted for, which we think are a common cause of obesity and critical illness. And we have represented A star and Y star. Then we have a paper on risk factors for longer length of stay in patients who required escalation of care. And all these are common causes of severity of illness as well as worse outcomes. Then we recently published a paper on analgesia and sedation at terminal extubation. This is basically measuring the amount of opioids you received after terminal extubation and time to death. Again, the common causes, and in this also I have shown the variables which are associated with just the exposure and the outcome, but not both. So they're not adjusted for, and why they're not adjusted for. And this is the more recent JAMA paper on early steroid administration with outcomes. And here I have tried to use this as a surrogate for randomized trials. So whether or not after adjusting for all these variables, the idea is that I am assuming that the two groups are so similar that whether or not they got steroids was by random chance. And what we're trying to see here is whether or not you got steroids within first 48 hours, first 2 days of hospital admission, and their outcome or disease resolution, which was measured by length of stay. So a lot of biases in this kind of study, but DAG makes it very, very transparent on where the biases may be, and what all factors we control for, and how did we measure it: measurement bias, unmeasured confounding, and inadequate confounding, race, socioeconomic disparities. And then there are other people's also published DAGs, and they all look slightly different, but the idea is the same. This is a association of atopic dermatitis with sleep. This is a race and health insurance. This is published by Erica. Erica was actually one of my co-author in one of the COVID papers, and she's the first one who told me about DAG, and at that time I also was like, what's a DAG? So and lastly, credit. So I've explained before, most of the examples I have here are borrowed from this excellent course in edX by Miguel Hernan. He's a biostatistician at Harvard. Then Judah Pearl is a computer scientist, and he has developed this causal language. His book of Why is an excellent book. He also written a lot of more technical books on the topic, causality, and causal inference, but book of Y is written for general population. And then there is Brady Neal is also somebody who has done a PhD in causal inference, and he has an excellent course, Introduction to Causal Inference. It's a little bit more mathematical than the edX course. And then most of the most of the DAGs are built using DAGity software. Thank you, and please feel free to um, send me any questions on my email. This is also on YouTube and Twitter.